Greetings, everyone. This is Statistical Inference. At Virginia Tech, we call this Stat 5114. I'm going to be presenting the next two lectures, this one and Fridays, in this format. But I also want to point out that this is a face-to-face class as well. So we'll be meeting for face-to-face sections in Hahn North 130. I'm in Hutchinson currently. I'll give you all of my logistics in a moment when we go over the syllabus, but I would like to just get to the nitty-gritty and tell you what this class is about before I go through the full structure of the class. This is important. If you're going to be joining us in person, this is the room for you. So that's a 1 there, 130. We're going to have a lot of modalities to this class. So my intention is to do everything face-to-face so long as everybody can maintain the Virginia Tech health and safety standards, myself included. So I'm in this room in Hutchinson Hall, right down from my office. So my office is in Hutchinson Hall, and periodically I'll host office hours there. And so I have a whiteboard in a foyer. Out in front of my office, we wouldn't be able to put more than 2 people in there at a time, but I will be conducting myself face-to-face. The lectures that you are viewing off of this YouTube page, the Lehman lectures, will be persistent throughout the semester. So you can take the class in either modality almost. So you can attend class if you would like, and you'll get all the interaction that would be normally accompanied in my classes. But if you have to distance learn, these videos will be your support. We'll also do Zoom sections. I sent out an email to you earlier yesterday, and it has a Zoom link for the class, and we'll be using that Zoom link for review sessions, primarily. Sometimes I might need to meet with you on Zoom. We will use that link exclusively. There's a password that's also sent with you, so if you need to use it, you should be able to come in. I think I set it up so that you can come into the room before I get to the room as well. If you guys want to use that link to conduct some sort of student get-togethers, feel free. So you can use it as well. I think you could act as host. Preferably, we can just set up another link. Again, that link's going to be persistent throughout class. What I intend to do with it is my review sessions. So every 2 weeks, which is going to coincide with when your homeworks are due, I will come on in the evening onto Zoom, and either I'll do it here, some classroom around here, or I'll do it at my house on my whiteboards that I have in my house. So I use a mixture depending on what seems to make the most sense. So I live in the country, so my Zoom links don't always work. So if the weather is bad, I'll probably be Zooming from here for review sessions. If the weather's good and I don't see a big hang up on my bandwidth, I might do it from home. So you'll get to see where I live. Again, review sessions every 2 weeks. They will be virtually hosted. So synchronous, meaning that we'll do it all together. We won't record those. It'll be a help for your homework. I'll also do face-to-face question answering. So if you do have struggles and it's right after class, we can make our way over to my office space and answer your questions after class. So our class is from 9 a.m. to 9:50 typically. On the first day of class and the second day, the Wednesday and the Friday, I will be joining Zoom at 9:30 to answer any administrative questions that you might have. If you want to just introduce yourself, that's fine too. I love that. Otherwise, we can meet up face-to-face in Hahn on Monday. So that starts up on the 25th of January. Right now, everything is mandated to be virtual. I think what the idea is we'll be able to pivot if need be. So it does seem like there's a bit of a surge in the pandemic. That's to be expected. It's winter. We'll see how it goes, but our primary concern is safety here. In the face-to-face sessions of class, you will be required to wear a mask. So here is one of my masks. I think we're all used to this now. When I teach face-to-face, I will be wearing a shield. And so the audibility on the lectures goes down ever so slightly. So I did this last semester and it seemed to work out. But we'll just mix up all the modalities and use everything and see what makes sense. So videos hosted on YouTube, Zoom, review sessions every 2 weeks, Zoom to powwow with you guys periodically. We will do all the things that we would normally do in class. So again, the primary objective of this class is to learn statistical inference. So without going into all of the logistics, I'll save that for a couple minutes down the road. I want to just talk about what this class is even about in the first place. So statistical inference. And the question is what is inference? So what does it mean to infer? And since I know nobody's going to answer my question, I'll answer it for myself this time. It's to learn. So this is really to learn. Or deduce something. So what do we do as statisticians? We learn from data. And so this is going to be from data. Now, in a lot of ways, an inference problem is the inverse of a probability problem. That might seem confusing to you at first because we do use probability in our inferences as well. So, but let me just show you through a basic setup. So a probability model, and I've written it down, is this thing right here, this function. And so the way I've chosen to note this is that this is continuous. And this function right here is going to have a fixed theta. So theta is known and fixed. And what this symbol means right here, sampling IID, and I'll just give you a little bit of a glossary as we go. Most of you will know this. This means independent and identically distributed. So the independent means that given knowledge of theta, so I want to just write in that this requires knowledge of theta for these to be independent. So I'm just going to make a note right here, conditional on theta. And that's what this bar means. So everything to the right-hand side of the bar is a conditioning parameter. So these are usually referred to as parameters of the model. So param. And this could be plural. That could have quite a few different parameters in there. And so I'll just write parameters. So what we're saying when we say that data is independent and identically distributed, we're saying conditional on theta, I can write down and draw this curve. At least conceptually I can do it. And then I'm going to sample these without knowledge of my previous samples, and I'm going to do it exactly the same every single time. So that's the identical part of this, that I don't change the process. So here's what it looks like. I'm going to randomly grab a number, and the weight I'm going to put on each number, so this is x right here, and my numbers are distributed along this axis. I probably should be polite and tell you where x lives. X, I'll just say, lives between negative infinity and infinity. And I should probably tell you where theta lives, but for right now we're going to assume that it's fixed and it's been imputed into the model correctly. So I'm going to sample values along this axis, and I'm going to put weight on them that's proportional to the height of the curve. And in intervals, I'm going to put weight in intervals proportional to the area in this area. So whatever this area is, that's going to be how it's going to be related to the probability of grabbing x's in that interval. So say this number right here was something like 0.62, and that's the area of this interval. What it would mean is that with probability 0.62, I'm going to sample a number in this interval. So that's a probability sampling model. This has another name, IID. Sometimes we call it simple random sampling. These are synonyms. So SRS, simple random sampling, is IID sampling, meaning that if I were sampling from a collection of discrete numbers and I selected a number out of that grouping, I would select the number, I'd write it down, and then I would replace that number. So this is sampling with replacement. So sampling with replacement. The book that we'll be using, Casella and Berger, and I'll go through those logistics in a moment, goes into some amount of detail about this and says usually in statistics we sample without replacement, and that's true. And they show that if at least the population size is large, that it's virtually the same thing, and that is true. We'll go into more nuanced technical details in future classes. Okay, so a probability model is basically showing you the process and describing mathematically through this function and through the rules of probability how these x's are likely to be sampled. And so given theta, I place a probability measure on x. So I just want to point out what this word is, probability. And this can be written down a couple different ways that are identical. I'm going to show you Kolmogorov's way of writing down what a probability space is. Or not a probability space, just the properties of a probability measure. So that's a little bit different. I don't think we need those technical details in this class. I don't think we're going to make this measure theoretic. But if you ever want to discuss it at that level, I'm happy to do so. Just don't want to bog our vocabulary too much, although I might use terms that sound measure theoretic. But probability, the properties, are usually something like this, and there are different ways to write them down. But I might say the probability of the entire space so usually we might give that a symbol, omega. I might say something like theta is in omega. This is equal to 1. So probability measures live between 0 and 1. So probabilities of any x's are going to be greater than 1. Or, sorry, greater than 0. And the whole space will add up to 1. So there's another property called additivity. I really like this property. It says that if I have a union of a bunch of instances, I goes from 1 to n. So this symbol is to union something, of a whole bunch of different random variables. So I'll just write down the random variable arbitrarily is r for my random variable. I think when I was glancing at this last time, they use a or something like that. But we'll just say a random variable. So the probability of this thing, and I need to put a condition on this, if the ri's don't overlap, So for every random variable, they're non-overlapping. What I mean by this is the probability of Ri intersected Rj is equal to 0. Right here, that they don't intersect each other. So these are all mutually exclusive random variables. So if this is the case, so let me just kind of show you a picture of this maybe. What I'm thinking of is I've got my space, omega, and I'm going to just partition this. So I'll call this R1, this R2, this R3, this R4, this R5. So I've got this partition on my space right here. If I added together all of these, the probability of R1, R2, R3, R4, R5 would equal to 1. But if I just took a subset of them, and I wanted to know what's the probability of maybe these two, they would just add together because there's no overlap. So this is going to be the sum, I goes from 1 to n, of the probability of each r. I'm expecting that this is all reviewed for you, that you know what the properties of probabilities are. They add together if they're mutually exclusive. And the last one is the complementary property. So the complementary property is the probability of some region, I'll just use it as R generally, is equal to the probability, I'll say it like this, 1 minus the probability of its complement. So basic set theory. So the complement in my picture, let's say the complement of the shaded region, R5 and R2, is these other things. So those are the complements of the red stuff right there. So basic stuff. So that's a probability model. And in Stat 5104, you played around with these models. You learned a whole bunch of different probability distribution functions, and you learned what the properties of those random variables were. Basically, it's a class in calculus that's reserved to probability spaces. So meaning that the area under our curves add up to 1. So that's really the only difference. And then we start to see how we use these functions as modeling tools. So inference is the backwards process of all of this. So to infer something, it means to learn. And so what we get to see as statisticians is the collection of data. Let me just write down inference. And in some ways, this is the backwards process. As statisticians, we're investigators, we're detectives. What we get to see is things from the forward process. We get to see the xi's, but we don't get to see the function in advance. Namely, we don't get to know the parameters. In a real example, you don't need to know what f is. So in my class, I'm going to assume for most of our examples that we know f, and we don't know what the parameters are. In a modeling class, they'll teach you how to build f. And we can talk about that through examples, and I'll be giving you modeling tools throughout this class. So when we see a new distribution, we'll try to motivate it and say why we use those distributions. So we'll still dwell on probability and the properties, but what we're going to do is we're going to infer. And so what I mean by that is given the xi's, x1, dot, 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 all the way to xn, And I'll call this thing cap X. So that's my data. So the idea here is I'm going to get a collection of different X's right here that have been IID sampled. It doesn't have to be IID, but it's just easier to illustrate. We will be looking at models that are not IID. But if I just ended up sampling a whole bunch of values in here, I'm probably going to sample more in there than I would in this mode, just because there's less area here than there is here. So I keep getting values. If I sample a lot, I'll get to learn the shape of this function. I could take all these draws and draw a histogram of everything. And if I normalize my histogram so that the area under my histogram was 1, this histogram representation of the data would closely resemble this curve. Now, there's always a typical question of what's n? And what do I need n to be? Well, if you want to learn about this curve, you're going to need enough n so that this representation is telling you about features of the curve. And so it changes for every problem. So if we're going to try to learn parameters from very, very wiggly functions, we're going to probably need more data. If we look at very smooth functions, then we probably need less data. So it's very context specific as to how much data should we go and get. And we'll try to answer some of those questions in this class. So given all of this, we want to learn theta. So that's the goal. And that's what this class is mostly about. And we're going to quantify how good we've learned theta. So what we're going to do is we're going to develop an estimator for theta. And we're going to try to describe properties telling us how good those estimators are and which estimator should we pick. And we're going to try to answer all of the context-specific questions as to why you pick the estimators that you pick. So let me just look at a concrete example, and then we'll go through course logistics. So this is a pretty easy problem, but it's mathematically nuanced, even though it's simple to understand. So what I'm going to do is I'm going to grab a whole bunch of xi's from a uniform distribution. So a uniform distribution is aptly named. It's uniformly distributed between two parameters right here. So let me draw you a picture of this. So this is going to be my x's right here. I'll say x. That's my space. I'm going to sample x's between 0 and theta. And I'm going to have my distribution be uniformly distributed. So that means my sampling function is just a flat line. It's just a straight line between 0 and theta. What is the height of this? If I want the area under the entire space, so I'll just write down xi's, or elements between 0 and theta. And somebody might ask, do you include theta or do you include 0? I'm going to say probabilistically it does not matter. So whatever you assume there, we're going to get the same answer. So it doesn't matter if we know theta, if this includes theta or 0, or if it's just bounded by them. Not important in terms of the calculations we do. So I guess in my notation, I'm saying that we do not include 0 or theta. No big deal. So I might put an open circle right there to represent that. And so our function, f of x, given theta, is just this straight line. How big is this right here? This thing is 1 over theta. So theta times 1 over theta is equal to 1. And so that's why we know what the height of this thing is. Probability densities can never go below 0. Otherwise, we'd have all kinds of problems with our additivity function. So our function for this example our sampling function is really easy to play around with. You've got to know theta to be able to sample from it. So the xi's are coming from here. And I'm going to stop writing IID all the time. I'm going to make a rule for this class. If I don't write IID, it means it is IID. So if I don't say anything about it. Later on, we'll move to models where there's relationships between the random variables. We'll keep this simple right now, but maybe I'll just do this a couple times just to make us feel comfortable. Eventually I'm going to stop writing that and just assume everybody knows the rule to the class is stuff is IID unless I say otherwise. So I'm going to get a lot of different data points right here. So I'm going to, with probability proportional to whatever this small little slice is right here, I'm going to sample a value in that interval. So ultimately, I'm going to get a whole bunch of different values. They're not going to live on an identically distributed lattice because this process is random. I could end up getting a histogram representation of this function. Because everything is random, it's not going to be perfectly flat, but probably pretty close. And I think next time I'll simulate this for you, and we'll try to answer some of the lingering questions we're going to have about this problem. My question is how do you learn theta? How do you estimate? And there's a lot of ways you could estimate theta from this data. I'll give you two simple ways. And then maybe you can think about which way you think is better. And maybe on our Zoom catch-up session, we can have a small discussion about this. This example will linger throughout this class. So this isn't going to be the only time we see it. There's some interesting things that happen in this example. Namely, the parameter defines the edge of the space that we're sampling from. And when parameters live on the boundary of your space, it's harder to deal with them because we get information from only one side. So we never see any data right over here. And that does make things trickier. Usually it ends up diminishing a lot of the theory that we have about estimators. And so problems like this are conceptually easy, but in practice a little bit cumbersome. So the question is how do you estimate this? So what I would do is I would say my estimator, and I'm going to write down a function of all of my data, and it's made to estimate theta, so I'm just going to give some notation right here. And this data is the x1 to xn. I'm going to give that some notation. I'm going to call it theta hat. And usually in this class, I'll end up talking about our estimators in terms of a hat function of the original parameter. So the idea is that I'm supposed to build an estimator that estimates theta, and I'm going to give that some notation. Our typical notation is theta hat. So theta hat is not theta, but theta hat, if constructed well, will approximate theta. And we have to quantify what we mean when we say we approximate it. So there's a number of properties that you might already know about that you use to develop good estimators. So one way that you could estimate everything, so I'll say theta hat 1, is what I might do is I might take the average of all of this data. So all of these data points, I could average them. So let me give that a little bit of notation. So I'm going to say the average lies here. And all that is the sum of the xi's divided by n. I goes from 1 to n. Usually we call that x bar. So that's the mean, the arithmetic mean. And so we use that estimator quite often. Now, we know that x bar is nowhere close to theta, but we know that it's also probably right in the middle of this distribution. So maybe my estimator might be, since it's in the middle, what I would need to do is double it to bring it over here. So this point, the mean is approximating, it's close to theta over 2. And if you come closer, if you end up having more and more data and is big, we get closer and closer to that value. And so you might think that suggests an estimator, that I could take x bar and multiply it by 2. And this thing will be approximately theta. So you might like that answer. You might also know a lot of properties about x bar because of the central limit theorem. And we'll be covering that in the next couple days. That's in section 5.3 of our textbook. We'll go over that in a moment. I will tell you straight off, this isn't a great estimator. It's okay, so not great. But okay. And if you happen to think of that answer and you used it in the past, I wouldn't panic. As long as n was reasonably big, this is a decent estimator. Here's a property of this estimator, one property that we know. So property. And so this is what you're going to argue through to say you like your estimators. So one property of this estimator of theta hat 1 is it's unbiased. Maybe people like that. Personally, I wouldn't mind unbiased estimators, but I don't insist upon them. And we'll see that in this example. So what I mean by that is the expected value of 2 times x bar is equal to 2 times the expectation of some of the xi's divided by n. This is going to be, I can drag the sum out because everything's IID, and more so because expectation is a linear operator. And so these are all things you would learn in your probability class. So this is 2 times the sum of the expectation of the xi's, and I can drag the n outside too. And so you can complete the calculation. I'll just write this, is 2 over n sum, and here's where one of our properties comes in. Expectation of xi, these are all identically distributed. And so they're all the same. They have the same expectation. So since they are all the same, and I'm sampling the same way every single time, all of these expectations for all of these data points are the same. And so we can remove the index here. And what that means is that we're summing together the same function n times. So that becomes an n. And we know what the expectation of xi is. So we could even work it out. So the expectation of x, in this case, is going to be the integral of x times my density function, dx, between 0 and theta. So just as a reminder, expectations are just x, fx, given theta, dx. And this is going to be integrated over its whole range. So that's what the expectation is. It's a weighted average. It's a weighted average of these random variables right here with respect to how often they occur. So that's not too hard to do, and all of us could do that integral. I'll let you do it yourself. But those things cancel, and this is going to be 2 times, and this is going to be the expectation is right in the middle right here, so it's theta over 2. I'll let you handle that integration. Just up your exponent by 1, divide by your new exponent. So up my exponent by 1. This was a 1, so that becomes a 2. Divide by your new exponent, and then plug in your bounds of integration. So the 2 comes from dividing by your new exponent. Theta over 2. And so this is 2 times theta over 2, which is theta. And so that's what it means to be unbiased. In expectation, which may or may not be a property that we always want to use, I expect to be close to theta. So we're missing something, though, in our quantification, and we're not thinking about the stochasticity of this estimator. So this estimator is good with respect to being unbiased, but I could give you a lot of unbiased estimators. So another unbiased estimator that I could give you is a really bad estimator. So theta hat, I'll say 2, is equal to x3, just one of the data points. So the third data point that I sampled. This is a terrible estimator of theta. It does live somewhere in this interval. What you'll notice is the expectation, I should say 2 times it. The expectation of 2 times x3 is also equal to theta. So it's unbiased as well. So there's obviously more to this game than just picking an unbiased estimator. Here's another estimator. xn max right here. I'm going to define this to be the maximum of all of my data points. x1 to xn. So in terms of my picture, that's this data point. That's x, and in parentheses. So I'm going to put the parentheses in there to define the order. So just as a preview into, I think, the next section of our book, x1 with the parentheses means the minimal value. x2 with the parentheses means that you're looking at the second biggest value, so on and so forth. These are called the order statistics. So this is the maximal order statistic. So one thing we can say about this estimator is it's biased. It always lives to the left of theta. So these are unbiased. And this one is biased. But as n gets bigger and bigger and bigger, that value starts to nuzzle right against theta. Turns out I would use this estimator. It also turns out I would scale that estimator so I can multiply this by something and kind of budge it a little bit. The question is what would I multiply by? We'll come back and we'll look at that answer. Answers that are based off of the order statistics, and we'll compare them to these. So there's 2 things that we need to consider when we build estimators. It's 1, on average, what do you expect them to do? But for any given estimator that you're going to compute, we have to be concerned about how wildly it varies. So this estimator right here, 2 times x3, while it's unbiased, it varies a lot. It's all over the place. So if I repeated everything, I might have x3 over here, the third draw. But on another sampling of n data points, x3 might be way over here. So it moves a lot. And so we don't want to build estimators like that. So I'm going to come back to this example for Friday's class. But without further ado, let me just say a few things about the logistics of the class. And I'm going to go through this rather quickly because I think it will be a good idea for us to visit this in person. So I'll probably say a few words on Monday as well about the syllabus and expectations. But let's just begin. I'm going to power up for a second. Normally this would be a good time for me to take a sip of coffee. Unfortunately, I forgot to bring my coffee. Okay, I see it coming in. Okay, I just want to point out the timetable for this class. This is our class right here. Stat Inference is a quick reminder. This is going to be meeting 9:05 to 9:55. So I recall saying 9 o'clock to 9:50. Shift that over 5 minutes. So I had a biased representation, but not too bad. Not too far off. So 9:05 to 9:55. Also, we meet in Han North 130. So that's across the drill field. I'll also point our attention to the mandated final exam time slot by the university. I don't get to switch these. These are always picked for us. I'm not sure what's going to happen in this class. Last year I gave a take-home final, and if the pandemic is ravishing Blacksburg, then I'm going to switch to an online final, but my intent is to do this in class. So please mark your calendars. The exam time is May 11th, 2021, and I apologize for this, 7:45 a.m. So if we can do it in class, I would like to do it in class. We'll adjust as necessary. For the midterm, I'm going to wait until Monday that you guys are all here, and then I can schedule the midterm with you guys. I'll take a poll, see what works. We'll also schedule our review sessions at that time. So I'll take a poll, see what works, and we'll get our schedule down. Make a special note of this one. Okay, so that's the most mundane. Of everything. I had sent you an email. You can actually see what time it is right now. So I sent this 3 hours ago. So it's Tuesday for me, but you'll be watching this probably on Wednesday. I sent out this email and it has a number of resource links in it. So we're going to be hosting a Slack discussion board. Please sign up for that. Just follow the link and you'll be able to get in. What I'm going to do for the review sessions is I'm going to ask you to post questions before my review session so that I know what I'm supposed to answer for you. It'll make it efficient for us, and a lot of times there's overlap in people's questions, so it'll help to keep us organized. Please do that as we go, and I'll try to stay on top of answering it. I'll have a couple different rooms in Slack that you can check out, but there is a link for Slack right here. If you just press on it, it will take you to the page. And here's the page right now. So a lot of you have already signed up. So about 10 of you guys, you're all listed here. This is me. And I've added a few different channels here. So review questions, for whatever day we set up our evening reviews, you'll send your questions to this channel. More general questions right here. And if you just want to ask random questions, maybe to the class, you can post in here. And if you guys have suggestions on other channels that we might want to look at, I'll add it for you, no problem. So there might be conversations you want to have amongst yourselves, and there might be conversations that you want to have specifically with me. And there might be conversations that pertain specifically to the review session. So that's how we're going to mostly use this page, is for the review sessions. There's also my web page as well. So my web page, if you click on that link, it will bring you here. And you will navigate to our slot. So I post a lot of my classes here from the past. Usually I'll leave up the old assignments. I've cleared this one out for our class. And this is our basic structure of the class. tells you basically what I said over here. We're going to learn how to figure out what theta is and quantify it. But we'll be studying a lot of different methods in this class. So I will be talking about classical statistics and Bayesian statistics. We might even entertain a few other types of methodologies. But mostly we'll be looking at the two popular ones. We'll show when they're similar and when they're different. In terms of estimation, Bayesians and classicists and frequentists, and you can be a frequentist if you're a Bayesian as well, they oftentimes agree. It's when we get into hypothesis testing that you see a gross disagreement between the different camps. So it's important to understand why that arises. Anyway, we're going to be looking through inferential methods. All branches of statistics will be considered. Order stats and their distributions is coming quickly. Approximate asymptotic methods, and computational methods. Sometimes they're the same. So we're going to be looking at a lot of different branches of stats, computational approaches, and then limiting theory as well. And we'll try to decide when each method is appropriate. We'll look at some principles of inference. That's chapter 6. We're not going to dwell a lot on the principles per se, but we will discuss them. As I said, classical and Bayesian treatments of inference and hypothesis testing are going to be explained. And we're going to be going through interval estimation, confidence coverage, pivots, and we might introduce some more modern methods like simulation methods. Your syllabus is here, and I will fill in the exact logistics for our class. So I've suggested in here that we're going to have 2 midterms. Well, I want to take back what I said earlier. We're going to have 2 midterms. One will be take home, and one will be in class. So we'll need to get dates for those. These are not the right dates. They're the dates I used last time. On Monday, I'll be polling the class for that. So if you can't attend on Monday, I'll jump on Zoom as well as we're doing the polling, and maybe we'll be able to figure everything out. Lecture times, this is the right time, wrong room, so we'll update that for you. And I do have a TA for the class. That's going to be Mohammed Salam. And I will update all of these logistics. So these are going to have to change depending on the information you guys give me. So the primary readings for the class is Casella and Berger, Statistical Inference. It's what most graduate schools around the country use. So it's a good book. Like most books, sometimes it's hard to follow when they're going through so many different examples and so many different branches of statistics simultaneously. And so my job is going to be to help break down what the text is saying. We're not going to follow exactly linearly chapters 5 through chapters 9. We're going to jump around a little bit. I want to point out that the Virginia Tech Health Standards, if you have any questions about them, read through this. Virginia Tech has a set of wellness principles, and they say what I said at the very beginning of class. So wear a mask, cleanliness is important, we have to maintain our social distancing standards, and if we can do all of that, and everybody else can do all of that, we get to continue throughout this semester. So uninfringed. We'll see what actually happens. So textbook, computing, I don't really care what you use. We will have a number of computational assignments. I'll use MATLAB for all of my examples. A lot of you might prefer R, and some of you might even prefer something else. So I'll let you decide what works for you. You could use C and C++, add-on functions. I usually see it as it's a good opportunity to learn something new, so practice your computation. And the more you do that, you'll be more flexible and be able to jump into other frameworks, different computational packages pretty instantly. My biggest recommendation is pick something with graphing facilities, because I'm going to ask you to graph a lot of stuff. Okay, academic honesty, you can read through that right there. So on midterms and finals, you can't work together, but I do encourage group work We will have a couple projects. I encourage you guys helping each other out. And homework. I expect that you guys will talk about the homework problems together. So the same thing is true in this class as it is anywhere else. Do your own work. If you need help, get it. But make sure you understand it at the end of the day. And so don't copy people's solutions. Have them help you with the conceptual parts. Something you're having difficulty with. If they can't help you, I'll be able to help you in a review session. And so let's just make sure that we maintain the high standard that's expected of us. If you suspect your work's been incorrectly graded, basically come and see me. Send me a note and we will get it corrected. I would suggest reading through these right here. The following claims will not be considered for regrading. Arguments about the number of points lost. I don't mean to be that harsh about it. What I mean when I say that, if I've incorrectly graded it or totaled it, absolutely. So we can discuss that. What I mean when I say that is, if your friend gets a 99 and you get a 98 and you think that it's about the same and you get a -1 on something, I would suggest not worrying too much about it. If it does bother you a lot, fine, come and see me, we'll get it worked out. The grade breakdown, I'm going to make it uniform. So homeworks, potential quizzes, I think with the virtual format, that will be nearly impossible. So this is really just going to be homeworks. 25% of your grade. You should be able to get nearly all 25% of that. The midterms and the finals are uniformly distributed, so no huge pressure come the final. So periodically, if people are struggling, and I think that could be the case this year, so don't get behind. But if you are struggling because of whatever's going on with the pandemic, sometimes I provide some makeup opportunities on midterms and some projects to go and get you some extra credit. So we'll have extra credit sprinkled throughout the class. I would expect that you will be able to get the grade of your preference in this class. So we'll make sure you have all those opportunities. The last link I want to show you is our schedule. And this is going to be the most important resource for you. This is going to have all of our materials. So here's today. Start reading through chapter 5. We're going to introduce some concepts, which we just did. I want you to start reviewing sections 5.1 through 5.3. We're going to be dicing those up in the next couple weeks. There's a homework suggestion. That's going to be due in a couple weeks, so you don't need to start on that absolutely quickly, but probably by next week you'll start working through these problems. It's never a bad idea to start chiseling away at it sooner. I'll explain this written question. So I included a little proof that I wrote out with one sentence. I'll tell you what that says next week. Announcements. We have spring break days. We don't have an actual spring break this year because the university would prefer that we don't travel. And I think that that's logical. It's a little bit difficult knowing that you don't get a spring break. This is how they're distributing it. So on those days, we won't be having class. So 3 of these overlap our classes. So Monday, Wednesday, Friday. The other 2 are a Tuesday and a Thursday. I will point out, I will be hosting virtual lectures, not in person, on March 12th and March 15th. And so if you'll notice, this is a Friday, this is a Monday, and that happens to be a Wednesday. So I'll let you do whatever you want with that in mind. I will be providing these lectures. I just won't be attending class myself that week. So I've got some travel plans that I need to tend to. If you're having issues with going to conferences, I'm not sure that that's going to be a huge issue this semester. I'm not sure any conferences are live. But if you have any constraints in your schedule, feel free to let me know at the upcoming Zoom session. So I'll say with that in mind, that's all I have. We'll come back next time and study this uniform problem just a little bit more. I did give you a piece of code right here. So if you click on that, it will shoot up a MATLAB file for you. And we can look at it. I think we'll look at it next time. So I just threw something away there. Very typical. Let's try that one more time. So I'm going to grab that file, and I'll just bring it over to a text editor. So it's a bunch of MATLAB code. And so this code's pretty easy to read through. I have a bunch of stuff that's being computed, but this code runs and simulates this example that we were looking at previously. If you want to get a head start, have a look at that code. This is MATLAB, you can upload it. Sorry I didn't write this in R for you guys, so if you guys do want to write it yourselves in R, it's not too difficult. But anyway, we're going to be simulating this example, looking at a number of different estimators. So I've got the mean, I've got the range, I've got the mid-range divided by 2. And so I don't have the max per se written down right there. So all 3 of these estimators, I will tell you, are suboptimal in some sense. And eventually in this class, we'll get down to which estimators we want to look at. Somebody gave me a really interesting least squares estimator last time I taught this class, and so I coded that one up too. It also doesn't work too well. The assessment of these estimators is printed out to the screen through these fprintf commands. So I'll let you look at that, and I'm going to say thanks for your attention, and I'll see you on Friday.